Imagine a thunderstorm passing over a small town in eastern Montana. Say just a few inches of rain falling over fields and dusty roads outside a community of a few thousand people. That rain doesn't just soak into the ground and stop there. Instead, drops collect into tiny rills that flow into a dry ditch, then into a creek, then into the Yellowstone River. From there, the water drifts hundreds of miles across two states before joining the Missouri River, the longest tributary of the Mississippi. But this is just one piece of a much larger puzzle. The Missouri, the Ohio, the Arkansas, the Illinois, together with countless small rivers, form a network that drains nearly 1.2 million square miles of land stretching from Montana and North Dakota down through the heart of the United States to the Gulf of Mexico. It continues south, gathering momentum and merging with the Mississippi near St. Louis, eventually reaching the Gulf more than 2,000 miles downstream. Along its journey, that same water carries dissolved nutrients from farm fields, remnants of fertilizer, soil, or manure, so something as quiet as a summer shower in a Montana county can ripple all the way to a coastal ecosystem hundreds of miles away. In another scene, picture early spring in western Iowa, where farmers are preparing fields for planting. A sudden warm storm washes across fields where fertilizer was just applied. Water runs off tilled soil into roadside ditches, then into Small Creek A, which empties into Big Creek B, eventually spilling into the Raccoon River, a tributary of the Des Moines River. Downstream, the water joins the Mississippi at Burlington and continues towards the Gulf. Multiply that by 1,000 of similar events every spring across the Midwest, from the corn belt of Iowa and Illinois to the grain farms of Minnesota and the ranch lands of Kansas, and you begin to see the scale. Rain falling on a single farm is just a drop in a vast interconnected system of rivers and streams that touches dozens of states, hundreds of watersheds, and millions of acres of farmland. Every one of those small storms adds up, shaping water quality far from where it began, a reminder that the fate of a raindrop in the heartland is tied to the health of waters all the way to the Gulf. In parts of southeastern Minnesota, some families rely on private wells for drinking water. But in certain areas, those wells have tested high for nitrate, a chemical that can make water unsafe for infants. Parents are sometimes warned not to mix baby formula with tap water if nitrate levels are too high. Where does this nitrate come from? Often its journey begins miles away in farmlands across the Midwest. Every year, farmers spread manure and fertilizer to help grow crops. Under the wrong conditions, nitrogen can move through soil, into groundwater, and eventually into drinking water far downstream. Because of this, even something as simple as soil temperature can determine when and how farmers are allowed to spread manure, and that decision has become one of the biggest environmental debates in modern agriculture. Under every farm field lives an entire ecosystem of tiny living things called microbes. Microbes are organisms so small you can only see them with a microscope. Examples include bacteria, fungi, single-celled organisms, and there can be billions of these organisms in a single handful of soil. You can think of them like tiny workers that break down materials and recycle nutrients in the soil. When manure is spread on a field, microbes begin breaking it down. During this process, nitrogen inside the manure changes form. First, it becomes ammonium. Ammonium is a type of nitrogen that sticks to soil particles fairly well, so it usually stays in the soil. But another group of microbes then converts ammonium into nitrate. This step is called nitrification. Nitrate behaves very differently than ammonium. It dissolves easily in water, so when rain falls or snow melts, nitrate can move through the soil and sometimes end up in groundwater or nearby rivers and lakes. The speed of this process depends heavily on temperature. The microbes responsible for nitrification work much faster in warm soil than cold soil. Scientists studying soil biology have found that microbial activity changes dramatically with temperature. Around 70 degrees Fahrenheit, microbes are very active and nitrification can happen quickly. Around 60 degrees Fahrenheit, activity slows but still continues. Around 50 degrees Fahrenheit, microbial activity drops sharply. Below 40 degrees Fahrenheit, the process becomes extremely slow. Because of this, farmers often wait until soil temperatures drop below 50 degrees Fahrenheit before applying manure in the fall. That way, the nitrogen is less likely to convert into nitrate and wash away before crops can use it the following spring. In Minnesota, the Department of Agriculture maintains soil temperature monitoring stations across the state. Farmers can check online maps that show soil temperatures about 6 inches below the surface. In other states across the Mississippi Basin, similar monitoring occurs either through state programs or university extension services, helping farmers across Iowa, Illinois, and Wisconsin make similar decisions about manure and fertilizer timing.
One of the most common tools farmers use to prevent nitrogen from escaping fields is cover crops.
Cover crops are plants that are grown not for harvest, but simply to protect and improve the soil. Common cover crops in Minnesota include cereal rye, oats, radishes, and clover. These crops are usually planted after the main crop, like corn or soybeans, is harvested. They grow during the fall and sometimes early spring, keeping living roots in the soil.
Cover crops help manage nitrogen because they absorb leftover nutrients that might otherwise wash away.
Their roots take up nitrate from the soil and store it inside plant tissue. When the cover crop eventually dies or is tilled back into the soil, these nutrients are slowly released again for the next crop to use. In addition to reducing nitrogen loss, cover crops also help reduce soil erosion, improve soil structure, and increase organic matter.
Because of these benefits, some Minnesota manure management rules require cover crops in certain situations.
Especially when manure is applied during warmer periods when nitrate formation is more likely. However, cover crops also come with costs and challenges for farmers.
Planting them requires additional seed, labor, and equipment passes across the field.
Seed alone can cost anywhere from about $20 to $50 per acre depending on the crop.
For context, the average farm in Minnesota is about 375 acres, and many crop farms plant several hundred to over 1,000 acres. That means cover crop seeds alone can cost anywhere from roughly $7,500 to $50,000 each year, depending on the size of the farm and how many acres are planted.
Farmers also need enough time after harvest to establish the cover crop before winter, which can be difficult in northern climates where the growing season is shorter. In some years, the crop may not grow much at all before freezing temperatures arrive. Another tool farmers sometimes use is a chemical additive called a nitrification inhibitor. These additives are mixed with manure or fertilizer to slow down the microbes that convert ammonium into nitrate. Remember that nitrification happens because microbes use enzymes to carry out chemical reactions.
Nitrification inhibitors work by interfering with those microbial processes, essentially slowing down the microbes responsible for conversion.
This means nitrogen stays longer in the ammonium form, which is less likely to wash away in a storm. By slowing down the conversion process, these additives can give crops more time to absorb nitrogen before it turns into nitrate and begins moving through water. However, nitrification inhibitors also add cost to fertilizer application. Depending on the product and application rate, they can add roughly $10 to $20 per acre to the cost of fertilizing a field. When applied across hundreds or thousands of acres, that can add up quickly. On a 500-acre farm, nitrification inhibitors can cost an additional $5,000 to $10,000 in a single season. Their effectiveness can also vary depending on soil conditions, rainfall, and temperature, meaning farmers sometimes pay for the additive without seeing a clear benefit. In Minnesota, manure spreading is regulated to protect water quality. Other states in the Mississippi River Basin have similar rules, although they vary in detail. Timing restrictions, cover crops, and inhibitor use are common strategies used throughout the Midwest to reduce nutrient runoff. From December through March, liquid manure generally cannot be applied to frozen or snow covered ground. When snow melts in spring, water can run across fields and carry nutrients directly into nearby streams and rivers. This is a concern across much of the northern U.S., wherever frozen soil coincide with manure application. For many fields in Minnesota, during warmer months, manure can usually only be applied if a crop is actively growing or a cover crop is planted shortly after manure is applied. This ensures there are plants in the soil to absorb nitrogen before it has a chance to wash away. During early fall, farmers must follow additional protections such as waiting for soil temperatures to drop below 50 degrees, planting cover crops, using nitrification inhibitors, or splitting nitrogen applications into smaller amounts. These practices are known as best management practices, designed to keep nutrients in fields instead of in waterways. Some areas in Minnesota have even stricter regulations. These areas are known as vulnerable groundwater regions. One of the most well known is southeast Minnesota's karst region. Karst landscapes contain underground channels, cracks, and caves in limestone bedrock. Because of these features, water can move extremely quickly from the surface into underground aquifers. That means if nitrate enters the soil in these areas, it can sometimes reach drinking water supplies much faster than in other regions. Because of this risk, manure application rules are stricter in these parts of the state. In parts of southeast Minnesota, studies have found that more than 8 to 10% of private drinking water wells exceed the federal nitrate limit of 10 milligrams per liter.
In some townships within the karst region, testing has found even higher rates.
With certain monitoring programs finding nitrate contamination in over 20% of wells tested. During winter, the restrictions become even stronger. From December through March, liquid manure generally cannot be applied to frozen or snow covered grounds. When snow melts in the spring, water can run across the surface of fields and carry nutrients directly into nearby streams and rivers. One of the main concerns about nitrate pollution is drinking water safety. High levels of nitrate in drinking water can cause a condition in infants known as blue baby syndrome. Inside the body, nitrate can be converted into another compound called nitrite. Nitrite interferes with the blood's ability to carry oxygen.
In infants, this can cause the blood to carry less oxygen to tissues, which can lead to breathing problems and a bluish tint to the skin.
Because of this risk, the U.S. Environmental Protection Agency limits nitrate in drinking water to 10 milligrams per liter. Infants are especially vulnerable because their digestive systems convert nitrate into nitrite more easily than adults, and their blood contains a form of hemoglobin that is more easily affected by this chemical reaction. Nitrate pollution also affects lakes, rivers, and oceans. When large amounts of nitrogen enter water, it acts like a fertilizer for algae. This can trigger large algae blooms, where algae grow rapidly across the surface of the water.
At first, this might not seem like a problem.
But when the algae eventually die, they sink to the bottom and begin to decompose. During this decomposition process, microbes consume large amounts of oxygen in the water. If too much oxygen is used up, fish and other aquatic animals can no longer survive.
These low oxygen regions are called dead zones.
One of the largest examples occurs every summer in the Gulf of Mexico, where nutrients carried by the Mississippi River fuel massive algae growth. The resulting dead zone can sometimes grow to thousands of square miles. In some years, the Gulf of Mexico dead zone has reached more than 8,000 square miles, roughly the size of the state of New Jersey. These regulations are not universally agreed upon. Many farmers say manure is a valuable fertilizer and that strict regulations can make farming more difficult.
Limiting fall spreading, for example, can require farmers to build larger manure storage systems, which can be expensive.
Large livestock farms often need manure storage lagoons or tanks that can hold 6 months or more of manure. These systems can cost anywhere from several $100,000 to well over $1 million, depending on the size of the farm and the engineering required. Smaller farms may struggle to afford these upgrades, while larger operations may need massive concrete storage pits or lined lagoons to meet environmental regulations. Environmental groups argue that stronger protections are needed to protect drinking water and ecosystems. Because of this, manure management has become one of the most debated environmental issues in Midwestern agriculture. So the next time you drive past a farm field in the fall, remember, what looks like a simple field is actually part of a much bigger system. Beneath the soil, billions of microbes are transforming nutrients. Above ground, farmers are watching soil temperatures and weather forecasts. And across the state, scientists, farmers, and policymakers are all trying to answer the same question: how do we grow food while also protecting the water we all depend on?
If you liked this video and this type of content, please be sure to subscribe, and thanks for watching.